Okay, let's look at factors influencing reaction rates. The first thing that influences reaction rates is what are your reactants? What is their nature? So, I mean, think about the bicarb, the vinegar versus the ship rusting, okay? There are factors in there that influence reaction rates. So, the nature of the reactants. Ionic compounds are going to usually react faster than covalent compounds, especially if you put them in aqueous solution. So those covalent bonds are nice and stable. If you have a large organic molecule, it's usually going to react slower, because if you think about that molecular geometry, when you make effective collisions, remember there's that example in there that shows how the two molecules can bump into each other, and that there's usually only one or two correct ways to position yourselves to have an effective collision. So if you have a large organic molecule and it's like long and skinny, and something's got to attack the bond on one end of it. If you imagine, for instance, a really long alkene, so imagine like a 6-chain carbon, and there's a double bond only on one end of it, and that gets bombarded by hydrogen. The hydrogen can bang all the way into that 6-chain molecule, but it can only sometimes, by statistic chance, hit the double bond. So the larger the molecule, they're usually going to react more slowly because there are fewer effective collisions. There's still hydrogen banging into that long alkene, but at the end of the day, the hydrogen doesn't always bang into where the double bond is. So the larger the molecule, especially organic ones, the slower the reaction rate, because there's fewer effective collisions. Please note here, when we talk about collisions, we always must mention this word effective. This word is very, very important. This word effective is very important in your answers. Please make sure that you put effective in your answers. And then the other thing with the nature of the reactants is metals. If metals are higher in the reactivity series, they will react faster than those lower down. Now, I've looked a couple of times through the curriculum, and this is not directly addressed by the CAPS curriculum, but like, for instance, if you think about it, you remember those alkali videos that I've showed you about sodium, potassium, rubidium, and how as you go down group 1, the reaction gets more and more explosive when you drop it in the water. So it starts out buzzing on the water, then it bursts into a flame, and then it trashes your container. So you can imagine there's a reactivity series with that. But all of the metals in the periodic table have been put in a reactivity series, and there's a way to remember it. Please send lions, cats, monkeys, and zebras into lovely hot countries. Signed, General Penguin. So if you have a look on here, potassium's really reactive, platinum is really unreactive. So if you think about it, this is why we make jewelry out of gold and platinum, because we can wear it and it stays shiny forever. Whereas silver will start going black if you wear it too much. Then we know that, like, for instance, iron rusts, but we make aluminium airplanes and we don't even have to paint them because they don't rust. Okay, so there's things in the reactivity series like this. We don't have to remember it, but when you come back to factors influencing reaction rates, the nature of reactants, where you are in the reactivity series, if you're a metal, will determine the reaction rate. So this is partly for interest. Okay, then the second factor after the nature of reactants is concentration. So have a look at this diagram here. What is concentration? If we have a look here, this is a low concentration. In this size box, I've got 1, 2, 3, 4 green things and 1, 2, 3, 4 red things. If these are gas particles and they're banging onto each other in the sides of the containers, they're not going to bang into each other very often. But if you look in the same size container over here, where we've got 8 or 10 of these things, they are going to bang into each other all the time. They are going to have a lot of collisions. A lot more collisions will then be effective. So increasing the concentration like this means you have more effective collisions, and if you have more effective collisions, rate of reaction is greater. So we look at concentration as the number of moles of the dissolved substance in a unit volume of the solvent. Okay, so this is an aqueous solution, and like in grade 10 and 11 we always talk about concentration in aqueous solution, but now we use pressure of a gas. is effectively concentration, because the number of moles of gas in a specific volume is like a concentration, and that's why sometimes going forward we can find the concentration of a gas using C equals N over V, the number of moles in the volume of the gas syringe or whatever container they're talking about. So you can see here, the more closely packed the particles are, which is high concentration, the more likely you are to have collisions. Very few effective collisions, a lot of effective collisions over here. So this here, this page, are you paying attention? This page is partly how you are going to answer the exam questions when they're asking you why does the reaction rate increase or why does the reaction rate decrease. Then you're going to swap the more for less, okay? But have a look here, this page and answering questions, this is like easy way to get your marks. If you increase the concentration of a reactant, there are more particles in the container, more effective collisions can occur between the reactants per unit time, okay? The probability of correct orientations and sufficient energy increases per unit time. These two here, you can usually get away with putting in here, more effective collisions can occur between reactants per unit time, because remember it is rate of reaction, so per unit time, and the more effective collisions must go together. So you make a statement, there's an increased number of particles in the container, more effective collisions can occur per unit time, the rate of reaction increases. So I hope you follow this. Okay, now the third factor is the state of division of the reactant surface. This is when you've got a solid reacting with either a gas or a liquid or whatever it is. When you have a solid reactant, the particles must bang into each other, okay? This is how a reaction occurs, is when particles bang into each other. So if this is a solid here, the only way these little red things can bump into the green things is on the outsides. So the reaction starts occurring and eating away the outside of the other reactant. The red reactant bangs on the outside of the green reactant. So it can only go as fast as there is surface area. But if we take this exact same amount of reactant and we chop it up into little lumps, so can you see it's like powdering it? It's like if this was a big block of sugar and I crushed it into little sugar granules. You can then see the little red dots can spread out and attack everything. They've all got a place to bang into it. There's much more surface area. So this will increase the reaction rate if you increase the state of division. So this is like if you've got calcium carbonate and you powder it, reaction rate is going to increase. So let's read what's here. Reactions can only occur on the outside of the solid. If the exposed reaction surface of a solid reactant increases, then the rate of reaction increases because there are more effective collisions taking place per unit time. So check this key phrases there. Reaction rate increases because there are more effective collisions per unit time taking place. So increasing surface area increases reaction rate because there's a greater surface for more effective collisions to take place per unit time. Then I think this is almost the last one, is temperature. So the average kinetic energy of a substance is directly proportional to its temperature. Remember from grade 10 we learn what is temperature. Temperature is a measure of the average kinetic energy of the particles. So if you look at a cold gas and you look at a hot gas, you can see in a cold gas these particles are moving slowly, and in the hot gas these particles are moving fast. And the moment you have faster motion, there are more collisions, and if there are more collisions there will be more effective collisions per unit time, and therefore you are going to end up with a faster reaction. So you can see here, this is the test for hydrogen gas. It's an explosive test. So this thing takes really long. If you start watching from the beginning here, okay, let's wait for it. Okay, there goes the water out of the picture. Here we've got hydrogen and oxygen. They can bang into each other without reacting. Okay, but now if we bring a flame in it, adding some heat energy, we heat up all of these particles and they now bang into each other much faster. Boom! And that's when bonds are broken and bonds are made, and the atoms separate and they recombine and they form water. And water as a chemical is much more stable than hydrogen by itself and oxygen by itself. So it just needs this little spark of activation energy to push it over the energy hill, and there you go, you've got water which is more stable. Okay, they like to show this on these Maxwell-Boltzmann curves. So Maxwell-Boltzmann curves, if you look over here, there's the number of molecules or the percentage of molecules or whatever, and their energy. So in any sample, if you were able to put your finger in and spy on the particles in a sample of water, you would find there are some really slow kids and there are some really speedy kids, but most of the class is just lurking around in the middle here. And this would be your temperature, because temperature is a measure of the average kinetic energy of the particles. Okay, so in the whole sample, some slow, some fast, most of them are about in the middle. Okay, so that's on the red curve. Look at the blue curve, it's exactly the same idea, but check where the peak is. The peak is at a lower kinetic energy. So on this curve, it's colder, it's at 20 degrees, still some slow, some fast, most in the middle, but the peak is lower down, less kinetic energy. Now where this is marked, the threshold energy, okay? This is the activation energy for any particular reaction if we look at the sample of molecules. And if we want to find out how many molecules have this activation energy or more, we have to find the area under the graph. So if we look at this blue curve, which is at 20 degrees C, there's the pale pink in here. This is the number of particles that have activation energy or more. On the red curve, you can see it's a much bigger area. It's this whole area here. So if you work this out mathematically with your lovely integration, differentiation, calculus rubbish, you will find out there's twice as many molecules at 30 degrees than there are at 20 degrees that have the activation energy. So the moment you heat up a reaction system, the rate of reaction increases because there are more particles with the minimum activation energy, and therefore there will be more effective collisions per unit time and reaction rate will increase. Then now the last thing, I thought that was the last thing, but it's not. The last thing is a catalyst. So a catalyst is a substance that influences the rate of a chemical reaction without undergoing a permanent change itself. So here's a nickel catalyst turning ethene into ethane. So you mix ethene and hydrogen gas, and this nickel catalyst somehow temporarily gets the hydrogen and the ethene to be properly situated with each other, so that the bond is broken in the ethene and the diatomic hydrogen bond is also temporarily broken and the new product forms. I don't exactly know how this works, how the nickel does it, but for every reaction that you can find a catalyst for, there's probably a slightly different mechanism. But basically it's helping the molecular geometry so that the ethene double bond is broken and the hydrogen can attach where it's meant to attach. Catalysts are very comparable to enzymes if you do life sciences. Okay, you have an enzyme and the enzyme's got a specific shape. They teach you the lock and key thing, and you have two substrates. These are the two reactants, and they come into the enzyme, and the enzyme makes sure they're in exactly the right position together, like this over here, and then they react faster than they would in normal life, and they go off. And this has got to do with the molecular geometry or the correct orientation. An enzyme and a catalyst both help the reaction to speed up without undergoing a permanent change. These are positive catalysts. There are inhibitors or negative catalysts, and these are like enzymes where you can put stuff in. So this enzyme is supposed to break this red thing up into two little hearts, but these little blue things fit inside the enzyme. And the moment there's little blue things inside the enzyme, the little red things can't go in there and be broken apart. So this would be an example of a negative catalyst. But we don't normally deal with this. We usually just deal with positive catalysts, which help everything go faster. So how does the catalyst work? It decreases the activation energy and increases the rate of reaction. We can distinguish them as homogeneous and heterogeneous. Homogeneous when everything's in the same state, heterogeneous when they're in different states. A lot of the catalysts are heterogeneous, like platinum and hydrogen gas. And if you think of all those chemical processes, the Haber process, the contact process, the Ostwald process, all of those processes usually have some kind of a metallic type catalyst, which is a solid, and the reactants are gases. So let's look again at this Maxwell-Boltzmann curve. Now here we've only got one curve. Look here, there's a number of this is like the number of particles with that energy, and this is their kinetic energy from low kinetic energy to high kinetic energy. And on this example we've only got one curve, okay, and here is the normal activation energy. So if you check, okay, by the way, there's only one curve because this is one single temperature. So if you check at this specific temperature and you draw in the activation energy, only the little green area under the curve has got particles that can react. But the moment you put a catalyst in here, that catalyst lowers the activation energy, and now check your area under the graph is now huge, and this means many more particles have the activation energy or more, so they can have more effective collisions per unit time, so the reaction rate goes up. So this is your Maxwell-Boltzmann curve, and here is what it looks like on one of these reaction progress graphs. Okay, so we have potential energy against reaction progress. We know that this is an exothermic reaction because here's delta H over here. So usually when a reaction occurs, we must put some energy in to push up to the top of this hill to this activated complex, and then this is where the bonds are broken and new bonds are formed, and we come out to the products. Okay, so you know the pathway goes up and down, and this is a big hill that requires a lot of energy to start, but then shoomp, it releases energy. If we put the catalyst in here, the catalyst's like, hey, it's a detour. So all of these particles go, ooh, look, easy pathway. And only a little bit of energy goes up this hill, but shoomp, when you come out, you've got the same enthalpy of reaction, because whatever was the reactants is going to make the same products. They just went a different way. It's like driving Hoodspray. This is like driving Hoodspray Palabora one time. This is like driving Hoodspray Zanine Palabora. Okay, if you can imagine that, or like Hoodspray Joburg Palabora, and this is just Hoodspray Palabora. You still ended up in the same place, but the one way was easier. Okay, we'll look at the graphs later.